All right, today we are going over lesson 20, something called antiderivative. And so far, so far this semester, we have discussed all things involving just the derivative. Where there would be some cases where you're given the derivative, like for example, if you're given acceleration and you have to go back and find the velocity and the original position equation. So if you have to recover a function from a derivative, then the process of undoing or reversing is called the antiderivative. So let me read just to back up what I was saying. Many problems require that we recover a function from its derivative or from its rate of change. And as I mentioned, for instance, the laws of physics tell us the acceleration of an object falling from an initial height, and we can use this to compute the velocity and the height at any time. More generally, starting with a function small f, we want to find a function capital F whose derivative is lowercase f. And if such a function, capital F, exists, then it's called an antiderivative of lowercase f. Antiderivatives are the link connecting the two major elements of calculus, derivatives and integrals. Here's the formal definition. Pretty much what I said, but in more tighter, cleaned up terms. The process of recovering a function capital F of x from its derivative lowercase f of x is called antidifferentiation. We use capital letters such as f to represent an antiderivative of a function lowercase f, g to g, and so forth. The mean value theorem guarantees that any two antiderivatives of a function differ by a constant indicated by capital C. So if you're going backwards, you're given the derivative and you're trying to find the original function, then there's usually some arbitrary constant that you have to take into account. So the functions x squared plus c, where c is an arbitrary constant, form all the antiderivatives of lowercase f of x equal to 2x. Theorem 8. If capital F is an antiderivative of lower f on an interval I, then the most general antiderivative of lowercase f on I is capital F of x plus c, where c is an arbitrary constant. Now we know the power rule for derivatives. In which we move the original exponent to the front and multiply it by whatever constant's out there. And then you subtract 1 from your original exponent. To find a general antiderivative, you're going to reverse the power rule. So over here with our general function, instead of subtracting 1 like we did here from the original exponent, We'll do the opposite. So the opposite of subtraction is addition. And over here, instead of multiplying our exponent by whatever constant's in front, the opposite of multiplication is division. So you'll divide your entire antiderivative by n plus 1. And because we are taking the antiderivative or going back to original function, you have to put plus c to denote any arbitrary constant. Now, if you take the derivative of, let's say, 3x squared plus 7, 3x squared minus 11, 3x squared plus 99. Well, when you take the derivative of all three functions, the derivative of all three functions is exactly 6x. The derivative of all three constants is 0. If you notice, each constant is different. So when we go back and take an antiderivative, because the constant may be different, that's why we put a plus c to denote any arbitrary constant. Now let me copy and paste these problems to our paintboard. And hang on just a second, I'll share the paintboard with y'all. Find an antiderivative for each function. And we're going to take the power rule and reverse the process. So part A, question A, we have 21 x to the 20th power. And we need to find the antiderivative. Well, instead of moving your 20 to the front and subtracting 1 from it, you do the opposite. The opposite of subtracting is adding. So we will add 1 to our original exponent. And instead of multiplying 20 by 21, the opposite of multiplication is division. So we'll divide our entire antiderivative by our new exponent. Simplifying, we get 21x to the 21st power over 21. And the 21s cancel out, giving us x to the 21st power plus our unknown constant c. Your constant could be any number, positive 7, negative 84, positive 1 million. So if you check your answer, no matter what the constant is, its derivative is going to 0. Part B, question B. We need to find the antiderivative of x to the 7th power. Again, instead of subtracting 1 from the original exponent, we will actually add 1. Now, instead of moving your original exponent to the front and multiplying it by 1, understood to be 1, you do the opposite of multiplication, which is division. So we'll divide our antiderivative by our new exponent. Our final answer is x to the 8th power over 8. And don't forget your plus capital C. Let's look at question C. We have x squared plus 2x, or 2x to the first power, minus 48. Find the antiderivative. We're taking the power rule for derivatives and reversing it. So instead of subtracting 1 from the original exponent, we actually add 1 to it. So for our first term, that would be x squared plus 1. And for our second term, that would be x to the 1 plus 1 power. Now, to deal with the constant negative 48, we can rewrite that in terms of x as well. Negative 48 can be rewritten as negative 48 x to the 0 power. We didn't change the value because x to the 0 power is 1. So we do the same thing here, undoing the power rule. You add 1 to your original exponent. Now, instead of moving each exponent to the front and multiplying it by a constant, you do the opposite. The opposite of multiplication is division. So we'll divide each term by our new exponent. Simplifying a little bit, we have x cubed over 3 plus 2x squared over 2 minus 48x over 1. And for the second antiderivative, when we cancel out the 2's, we get our final answer of x cubed over 3 plus x squared minus 48x, and don't forget your plus c. A smart way to check your answer is by taking the derivative of it. Let's look at the next set of problems. Second question A, we have g of x equal to 1 over x to the 8th power. And in order to find the antiderivative, let's rewrite our fraction with a negative exponent. Now, using the antiderivative rule, instead of subtracting 1 from your original exponent, you add 1 to it. So that would be negative 8 plus 1. Instead of moving the negative 8 to the front and multiplying it by 1, you do the opposite of multiplication, which is division. So we'll divide our entire antiderivative by negative 8 plus 1, our new exponent. So this will be now x to the, negative 7 all over negative 7. And because our original derivative was a positive exponent, our antiderivative, let's do the same thing. So this will become negative 1 over 7x to the 7th power. And don't forget your plus c. And that is your antiderivative. Or you could also call it your original function. And let's look at a second B question. Second B question, we have g of x equal to 1/5 x to the negative 2/5 power. To find the antiderivative, take the power rule for derivatives and reverse it. So that means here, add 1 to the original exponent, and instead of moving your exponent to the front and multiplying it by any visible constant, or any constant there, the opposite of multiplication is division. So you will divide by your new exponent. Now 1 is the same thing as 5 over 5. Just makes it easier to simplify. So we have up top x raised to the 3/5 power all over 5 times 3/5. And one final thing we can do before adding our constant is cancel out the 5's. And our final antiderivative is x to the 3/5 over 3 plus capital C. That's all you're doing so far when you have to find the antiderivative. You're taking the power rule and performing the operations in reverse. First half of Calculus 1, deals with derivatives. The second half of Cal 1 deals with integrals. Now, an integral is just what we just got through doing. It's an antiderivative. A special symbol is used to denote the collection of all antiderivatives of a function small f. Definition: the collection of all antiderivatives of lowercase f is called the indefinite integral of lowercase f with respect to x, and is denoted by a little curly s, and that's the integral sign, f of x, and then dx is the change in x, quite simply. The function lowercase f is called the integrand of the integral, and x is known as the variable of integration. So we are doing pretty much the same thing as before when we had to find the antiderivative. It's just worded and shown or depicted differently. So let's start with the first one here. And this is still less than 20, the antiderivative. Find the indefinite integral 8x plus 3 dx. I'm just going to separate our problem into two separate integrals. We have 8x to the first power dx plus the integral of 3 dx. Now that 3, I'm going to rewrite it like we did in an earlier problem as 3x to the 0 power. Now, there's a rule of there's a rule of integrals, period, that you can move constants to the front of the integral sign. So we'll go ahead and do that. Now we can use the power rule for antiderivatives. Just taking the regular power rule for derivatives and working it in reverse. So instead of subtracting 1 from each original exponent, instead you'll be adding 1. And instead of multiplying or moving the original exponent to the front and multiplying it by a constant, you do the opposite. So the opposite of multiplication is division, meaning here we'll divide each antiderivative by our new exponents. So first antiderivative simplifies to x squared over 2. The second antiderivative is x to the first power, or just x, over 1. Going back to the first antiderivative, 2 can go into 8 4 times. And our final answer is 4x squared plus 3x. And with indefinite integrals, you must put a plus c to denote any arbitrary constant. And as I mentioned earlier, a good way to check your antiderivative is take the derivative of it and see if you get the original problem. Let's look at some more. Okay, number 27. Again, before we take the antiderivative or integral, let's separate into two integrals. So we have the integral of 3t squared dt plus the integral of t over 2 dt. Couple of things we can do before taking each antiderivative. Move the 3 outside the integral sign. And do the same thing with the 1/2. Now we can undo the power rule, define each antiderivative. For the first one, add 1 to the original exponent. And instead of multiplying, the opposite of multiplication is division. So we'll divide by 2 plus 1. Do the same thing with the second integral. Add 1 to the original exponent. And you'll divide your antiderivative by your new exponent. That gives us now 3 times t cubed all over 3 plus 1/2 times t squared over 2 plus our c. To finish, cancel out the 3's and multiply your 2's. Our final antiderivative is t cubed plus t squared over 4 plus capital C to represent a constant. Let's look at the next problem. And this is not required, but it helps until you familiarize yourself with integrals. Because I have 3 terms, I'm going to split my problem into 3 integrals. And as I'm doing that, just moving any constants outside. So we have 2 times the integral of x cubed dx minus 5 integral of x to the first power plus 7. Now that 7, we can rewrite that as 7x to the 0 power. Again, we have not changed the value over there. We just rewrote it in terms of x. But because remember, x to the 0 power is 1. Next, find the antiderivative of each term by undoing the power rule. And that means instead of subtracting 1 from each original exponent, you add 1. So I'm doing that all together for each term. And instead of multiplying by your original exponent, you do the opposite, which is divide. So we'll divide each antiderivative by our new exponent. This will be now 2x to the 4th all over 4 times that 2 minus 5x squared over 2 plus 7x to the first power over 1. In our first antiderivative, 2 can go into 4 2 times. And let's get our final answer. X to the 4th over 2 minus 5x squared over 2 plus just 7x. And don't forget your plus c. Let me share with y'all the formulas for basic trig integrals. So give me 1 second to find that table. Trig integrals. Hold on just a minute. And just focus for now on the first, you can say the first 6 integrals. Let me go over each one with y'all. The integral of cosine u du is sine of u plus c. The integral of sine u du is negative cosine u plus c. Next, the integral of secant squared u du is tangent u plus c. Next, the integral of secant u times tangent u du is equal to secant u plus c. The next one in the middle, the integral of cosecant u times cotangent u du is equal to negative cosecant u plus c. And then the last one you need to know for now is the integral of cosecant squared u du is equal to negative cotangent u plus c.